Hello, my name is Thomas Bergmayr. I belong to the Institute of Structural Lightweight Design and to the Laboratory for Structural Strength Control at the Johannes Kepler University in Linz. I would like to welcome all the listeners of my presentation. First of all, I want to thank the European Structural Integrity Society for organizing this conference. The title of my talk today is Strain Measurements Along a Zero Strain Trajectory as Possible Structural Health Monitoring Method for Debonding, Initiation and Propagation in Aircraft Sandwich Structures. At the beginning, I want to give a short overview about the motivation of using structural health monitoring. In order to make aircraft lighter, safer, and to avoid cost-expensive non-destructive testing methods to detect damages, results into the development of structural health monitoring. The field of structural health monitoring can be classified into several levels. Based on RITA, the levels are detection, localization, quantification, and qualification. Strain-based methods are classified into the static approaches, and this kind of methods can serve each of these previous mentioned levels. Strains are very sensitive to small structural changes, like damages. Strain sensing via fiber optical sensors or fiber breadcrusting sensors along lines have multiple advantages. This kind of sensors have a very high technological readiness level, and it enables a simple way to monitor strain data of large structures. Moreover, several experiments have shown that it is possible to integrate this kind of sensors easily into the composite structures. I will now show you how strain-based SHM methods can be applied at aircraft structures. As an investigated structure, an idealized aircraft spoiler is used. The basic idea is to optimally place a strain sensor in a way that is most sensitive to a change in a known plane strain state. Considering Moore's strain circle and assuming a plane strain state with the component epsilon xx, epsilon yy, and epsilon xy, the shear component vanishes in two principal directions. With respect to the x direction, the rotation angles of the principal strain states alpha1 and alpha2 are derived with the shown equation. Considering the same plane strain state, two directions exist where there is zero strain if the principal strain directions are tensile and compressive, respectively. This can be shown by solving the depicted equation in order to get the angles of the zero strain directions, beta 1 and beta 2. Compared to the principal directions, not the shear component is set to zero, but therefore the normal component. However, connecting the zero strain directions at various points of a structure yields to a zero strain trajectory. The zero strain method can be perfectly combined with the application of fiber optical sensors for the monitoring of large planar structures, as they are typical in lightweight design. A major advantage of the zero strain method is that for the considered loading of the structure the sensor measures no signal if the structure is undamaged. Therefore, no data storage is necessary. The second advantage is the high sensitivity if the structure gets damaged. The strain along the trajectory divides from a zero baseline to a finite value. As an example for demonstrating our SHM method, we chose a spoiler of a civil aircraft. The tested composite structure should imitate an aircraft spoiler on the scale of 2 to 1. Our considered idealized model also have a center hinge fitting and edge fitting like the original one, in order to enable a realistic attachment of the spoiler to the test rig. The idealized spoiler with a homogeneous ply layout, constant sandwich core thickness, is composed of glass fiber reinforced plastic face layers and an aramid Nomex honeycomb core, with a total thickness of 15 mm. The laminate is built up of 4 fabric laminate plies with a stacking sequence of 0, 45, -45, 0 degrees, with a total laminate thickness of 0.5 mm. In this investigation, a face layer debonding with different debonding sizes at the trailing edge is considered. The face layer debonding is semicircular shaped and located at the edges. At this slide, the extended spoilers during the landing process are depicted. The major task of aircraft spoilers is to slow down the aircraft. Therefore, the spoilers are fully extended during the landing process. This slide shows the finite element model and the displacements of the control surface caused by the airload during the landing. This slide should give an overview of the experimental setup of the investigated structure. The load was applied with a whiffletree in order to get a most realistic deformation, as occurring at the real spoiler at the statically most significant load case, which occurs during landing, as shown in the slides before. The ideal force introduction points of the whiffletree are found by means of a linear Fe shell model and by parametric optimization. The objective was to minimize the difference of the deformation between the reference Fe model of the real spoiler, loaded by the defined load case, and the Fe model of the idealized spoiler loaded by 4 local forces. To record the strains and displacement, a direct image correlation system is used. This result of this system is used for the validation of the Fe model. At this slide, the symmetric finite element model of the idealized spoiler is depicted. The test setup is modeled with the finite element method using the FEM software package Abacus. In order to reduce computation time and increase the accuracy of the direct image correlation system by means of reducing the monitored area, the simulation model is designed with the Abacus submodel technique. The implemented phase layer debonding at the sandwich structure was modeled with removing the tie constraint between sandwich core and skin in the damaged area. After performing a buckling analysis, the resulting buckling deformation is scaled and implemented as imperfection at the load analysis step of a successive analysis. To validate the numerical finite element model, several experiments are performed with the direct image correlation system. The figure depicted on the slide shows the comparison of the displacements along the z-coordinate of the numerical and the experimental results. The relative error between the displacements are approximately 5%. This comparison, as well as the strain results, clearly shows that the results from the direct image correlation system correlate well with the numerical results. To calculate the zero strain directions beta 1 and beta 2 according to the equation listed on the slide 2, the simulation results are transferred to MATLAB. The implemented algorithm uses the command stream2, a function which computes the streamlines from the direction vectors, and the function gridData to interpolate the finite element strain components on the trajectory. However, at the beginning, the zero strain trajectories at the pristine structure are calculated at the whole spoiler model, depicted on the left side. On the partial model, according to the submodel, the strain profile of 10 zero strain trajectories are calculated at various damage states. Subsequently, the strain profile along these trajectories are calculated at every damage state. The two diagrams show two strain profiles of fiber optical sensors at 5 different damage states. The figure shows that an inflicted damage leads to a change in the strain state and values, which cause a deviation from a zero baseline to a finite value. With increasing distance from the fiber optical sensor to the damage, the strain is converging to zero. The results show that the strain measurements along the horizontal zero strain trajectories are more sensitive than the vertical ones, considering the implemented damage as debonding. The results of the horizontal zero strain trajectories depicted on the right figure show one main disadvantage of strain measurements via fiber optical sensors without local resolution. Due to the fact that one gets the average strain along fiber optical sensors without local resolution, as a sensor output can yield to a situation where strains with different signs are cancelling each other out. This can lead to a situation where it is pretty difficult to measure and evaluate the damage propagation. To solve this problem, fiber break rating sensors with multiple sensing elements or continuous fiber optic sensors can be used. Using individual sensing elements with different break wavelengths enables simultaneously measurements of the strains using wavelength division multiplexing. The fiber break rating sensor delivers several strain results according to each break rating position, and a simple polynomial fit can be used to approximate the whole strain profile along the sensor, shown in the right figure. A simple 5-order polynomial fit calculated with 6 measurement points is made, which presents the whole strain profile in a very good way. A lower number of strain outputs, which leads to a lower order of polynomial experimentation, is also convincible for this approach, in order to reduce break sensor elements. However, with this technology, the damage propagation could be simply monitored due to the fact that an increased damage leads to a higher deviation from the approximated strain curve to zero. The exact placement of the fiber optical sensor or the fiber break rating sensor along the zero strain trajectory is a big challenge, because zero strain directions depends on the load case. Nevertheless, the numerical results depicted in these figures indicates that the directions of the zero strain trajectories are very sensitive and are well suitable for damage detection and monitoring propagation of damages, like the considered phase layer debonding. This figure shows the difference of the strains between the pristine model and the model of the first damaged state. The left figure shows the difference of the strains with respect to the x-axis, whereas the right one shows the results of the horizontal zero-strain beta 1 directions. The comparison clearly shows that the zero-strain directions are much more sensitive for monitoring damages to the high deviations in a wide range of the critical structure. Therefore, the damage is easier to detect with a strain sensor, even if the distance between damage and sensor is relatively large. In my presentation, I've shown how strain-based SHM via fiber optical sensors or fiber break rating sensors can be applied at aircraft sandwich structures. I have shown the strong similarity of the displacement distribution of the numerical and experimental results to validate my finite element model. Afterwards, I showed with numerical results that fiber break rating sensors with multiple sensing elements and in combination with polynomial approximation delivers the whole strain profile in sufficient accuracy to monitor the damage propagation. Afterwards, I showed that the zero strain directions are very sensitive in a big area. However, this presentation shows the high potential for damage identification and propagation monitoring using fiber break rating sensors along zero strain trajectories. In future work, I will validate this method with an experimental study. Furthermore, I plan to extend my investigation and also investigate and evaluate different damages like delaminations and holes. So I would like to thank you for your attention, and I will be happy to answer your questions.